Well, good morning to everyone. This is the first forum at the Midwest Superfest in Chillicothe, Illinois, near Peoria. And it's a nice Hamfest venue here. That's a big flea market out there and everything. I'm Carl, K9LA, and I'm going to talk about Cycle 25, Solar Cycle 25, and some thoughts on propagation for the next couple of years. I received my novice on October 61, so I've been around a couple times. I'm from Fort Wayne, Indiana. My wife is AE9YL. She's at home. She had some VE testing there, and also somebody's got to stay home with the 8 cats we have, so whatever. So let's get moved. Do I have to advance it from the PC?
Yes, I can move it closer to you if you want.
No, I can do it. It's okay. I'll just turn it around. There we go. Okay. So here's what we're going to cover. We'll talk about the latest data on Cycle 25. Just talk about some general knowledge about solar cycles and what happens during a solar cycle. Guidelines for the next several years. And then a summary. Now this afternoon, Tom, W9RY, is given a forum on all those numbers, all those space weather data. So that'll be a nice complement to what I'm talking about. Latest data. It's always good to go back and look at previous data. So what you're looking at is the maximum smooth sunspot number of all previous 24 solar cycles. Okay, cycle 1 began in 1755, and that was a little bit after, you've probably heard of the Maunder minimum, when there was just very few sunspots. But it was determined around 1749 that the data was good enough, so this is the recorded data. Now, what's obvious from that plot is we've gone through 3 periods of big solar cycles, okay? Cycles 1, 2, 3, and 4, cycles 8 through 11, and then in our lifetimes, basically 17 through 23 have been pretty big. What that also says is we've gone through 2 periods of smaller solar cycles. You can see cycles 5, 6, and 7 were kind of low. In fact, cycle 6 is the smallest in recorded history. Cycles 12, 13, 14, 15, 16 weren't as low as 5, 6, and 7, but they were still small. And the big question is, there's cycle 24 there, it's pretty low. It's the lowest in our lifetimes. Smallest, or the 4th smallest in recorded history. So was cycle 24 the prelude to another period of small solar cycles? Well, maybe we can kind of answer that. Here's the latest data. The cycle 25 is in thick red. We have about a little bit over 4 years of data, so that means we're pretty far into the solar cycle. Also on there are 3 other solar cycles. Green is cycle 24, the last one. Remember, it's the 4th smallest in recorded history. Orange is cycle 23. If you take an average of all 24 previous solar cycles, cycle 23 is kind of around the average, so that's an average solar cycle. Blue is cycle 21. It peaked in 1979, late 79. It was moderately big, and then the biggest one in recorded history, cycle 19. Who was on during cycle 19? Anybody else here? Well, I was, but oh well. This tells what my age is, I guess. Now, one of the things that you'll see if you look at what's going on is big cycles rise faster. You can see the bigger the cycle, the quicker it got to maximum. And generally, big cycles start a little bit bigger at solar minimum. It's kind of hard to see, and it's not looking at all the solar cycles, but that's just a general statement. Now, what's obvious is cycle 25 has surpassed cycle 24. Yay, that's good. That's good for the higher HF bands, 15, 12, and 10 meters. Will it make it up to an average cycle? I think what's going to happen from now on is cycle 25 is kind of going to oscillate a little bit and then start its descent in several years. I don't know if it's going to make it up to an average cycle, but that's okay because cycle 25 is big enough now to give us great propagation in the fall and winter on those higher HF bands. Now, people ask, is cycle 25 going to have one peak or two peaks? There's a plot of the monthly mean sunspot number. It also could be the monthly mean 10.7 centimeter solar flux. But you can see in cycle 24, it had two peaks, very definite peaks. In other words, a nice minimum in between those two peaks. Early on in cycle 24, the northern solar hemisphere was active. The southern solar hemisphere was not active. But then later on in cycle 24, the northern solar hemisphere, the blue, kind of calmed down, but the southern solar hemisphere kind of went up, and that's why cycle 24 had two peaks. Now, there's cycle 25, same monthly mean data. You can see up until a couple months ago, the two solar hemispheres were kind of working together. So I started telling people that I think we're just going to have one peak. Apparently the sun heard that because you can see what's happened in the past several months. The northern solar hemisphere is not as active as the southern solar hemisphere. So we'll have to just wait and see in another couple months what's going to happen here. Yeah. My best guess right now is still one peak, but there's a shot we'll have a second peak, which that'll probably help. It'll be hopefully a little bit higher than the first peak if we do have two peaks, which is good for the higher HF bands. Okay, the coming years. Cycle 25 is very similar to cycle 16. That's the blue curve there. And you can see where cycle 25 is in orange. So that green line is that smooth sunspot number of 80. That's what we need for good, consistent, day-to-day worldwide propagation on 15, 12, and 10 meters, maybe even 6 meters. So what it looks like is cycle 25 will be good out until the end of 26 or so, 2026. Now, if cycle 25 gets a little bit higher than what it is now, that's going to extend it out a little bit more. So we still have several years of really great propagation on the higher HF bands. Yeah, take advantage. For techs, they have 10-meter sideband privileges. You can work the world with modest antennas, like this little dipole at 20 feet, and modest power, 100 watts. So take advantage of it. Some general knowledge about solar cycles. There's a picture of a typical solar cycle. On average, it lasts about 11 years. Some cycles are longer, some are shorter. A to B is the rise time. On average, it's about 4 years to get to the peak of a solar cycle. On average, about 7 years for the decline. So 4 plus 7, that's where the 11-year average solar cycle length comes from. Now, the solar cycle is also called a Schwab cycle, because way back when, that's the guy who, hey, these things go like this and continual, so hey, I get named for it. There are other cycles in solar cycles. There's the Hale cycle. Anybody know what the Hale cycle is? Well, at maximum, the sun's magnetic field reverses. So it takes another solar cycle to get back to the original condition. So that's why there's really a 22-year cycle. And of course, the guy named Hale discovered that, so he got his name tied to that. Let me go back. Gleisberg cycle. Okay. That's the period between those big periods of solar cycles or the big periods of smaller solar cycles. So there's a kind of a 90-year pattern here going on. And that's called the Gleisberg cycle because there was a guy named Gleisberg. There's some longer ones. De Vries thinks there's a 205-year cycle. And then even longer one, Hallstatt, 2,300 years. You know, we start going back too far, we can't look at sunspot data because we don't have good data. But we can use beryllium-10 in ice cores or beryllium-10 in trees, or no, carbon-14 in trees and beryllium-10 in ice cores to get a picture of what the solar activity was many years ago. Now, I don't know if those are true periods or just artifacts of how we calculate that. But the sun's been around for quite a while, so who knows, it may have all kinds of periods to it. Now, we have to take the bad with the good. In other words, we have to just work through coronal mass ejections, coronal holes, and big solar flares, because that disturbs the ionosphere and makes things not as good. Of course, the good side is the solar cycle is at maximum and gives us lots more ionization for the higher bands and makes them open. Solar flares and CMEs are most prevalent around solar maximum, where we are now, so we got to put up with that. And coronal holes, they're most prevalent on the decline of a solar cycle, so that's going to be coming up. And in general, coronal holes are worse than CMEs, so in other words, take the bad with the good. K and A indices, I'm sure Tom's going to get into them, but I thought I'd put it on there. The K index is a 3-hour index. It's the maximum variation of the Earth's magnetic field in that 3-hour period. There are 8 3-hour periods during the day. It's a logarithmic number. Goes from 0 to 9. 0 is extremely quiet Earth magnetic field. To 9, very disturbed Earth magnetic field. And what happens, of course, is our magnetic field can screw up the F2 region of the ionosphere, which is responsible for most of our long distance and nighttime QSOs. Let's see here. The A index, that's an average of the 8 K indices. Now, it's a linear index. Goes from 0 to 400. 0 is extremely quiet. 400 is an extremely disturbed magnetic field. And you have to do some, translate the linear A index into the logarithmic K index, because you can't just average the K indices because they're logarithmic. So you have to change the linear, all of them, and then you can do what you need to do. When the K and A indices are very high, that generally means that the F2 region is screwed up, and that's not good. So what we generally desire is a K index less than or equal to 3. That kind of says things are pretty quiet, and the F2 region of the ionosphere is going to be okay. The K index of 3 translates to A index of 15. You can see that on the chart there too, how to translate A to K. So why are sunspots important? Well, the important thing is those white areas around the sunspots. Those white areas are called plage. That's from French for beach. Think of a white beach. And that's where the extreme ultraviolet comes from. The sun comes from those plage areas. And extreme ultraviolet is the true ionizing ionization, the true ionizing radiation from the, for the F2 region. Sunspots don't really do anything, and 10.7 centimeter solar flux does not have enough energy to ionize anything in the atmosphere. They're proxies for the extreme ultraviolet. And we generally can't measure extreme ultraviolet at Earth because during the ionization process, the extreme ultraviolet energy absorbed to knock off that electron. So by the time it gets down to ground level, there's no EUV left. So that's why we have to measure it above the Earth's atmosphere in satellites. And just remind, the F2 region is the one that's most responsible for our long-distance QSOs and also at night, because the F2 region does not go away at night. It gets reduced, but doesn't go away, thankfully. Here's an interesting plot. It's the maximum usable frequency on a path from K9LA and Fort Wayne to DL, which is Germany. It's at 1500 UTC, which would be either 10 or 11 a.m. my time, depending if we're in daylight savings or standard time. You can see what the MUF does in the summer. It takes a big dip, okay? But in the fall and winter, that's when the F2 region really gets going. Of course, in the summer months, we've got a lot of state QSO parties. We've got the IARU contest, field day. That's why generally in the summer months, we don't have good 10-meter propagation, unless it's sporadic E, which this year has been not too good. This year was not too good for sporadic E. Don't know why. We just don't understand it yet. The highest MUFs are in the fall and winter, and that's when most of the major DX contests are, ARRL, CQ, and I'm sure that's why they pick those fall and winter months, because they knew that the F2 region was very good. It's interesting, at solar min, or during the summer, the size of the solar cycle really doesn't matter that much. The MUF kind of bounces around 20 megahertz, 20, 21, 22, 18, and 19 megahertz. But in the fall and winter, of course, the size of the solar cycle matters quite a bit. And you can see, like in the 11, the November month, what the difference in the MUF is. It's dramatic. So we're coming into the fall and winter months. 10 meters is going to be consistent on a daily basis to the world with moderate power and moderate antennas. Now, CMEs can screw up the F2 region if they're Earth directed. There's a lot of them that thankfully are going out this way and that way and not at us. But if there's just a small spike in the K index, as an example, the top plot, you can see the K index went up to, looks like 7 for just 1 3-hour period. That can cause an enhancement. It can rearrange the F2 region ionization. The things are better for a short period of time. And what the bottom plot is the maximum usable frequency over the Wallops Island, Virginia ionosonde. You can see on the days that the K index was 0 to 4, and the MUF was kind of just a little bit below 40 megahertz. But on the day that the K index spiked up, it went up to more than 50 megahertz. So just be aware, if there's a single spike in the K index, or maybe a spike for 2 days and it's not real big, you might want to listen on 10 meters and 6 meters, just to see if there might be some F2 propagation. So why did our sunspot record begin in 1749? I kind of mentioned that earlier. The guy named Robert Wolf, he reviewed sunspot data back to 1610, and determined that we had good data starting around 1749. Now you got to remember the Maunder minimum was in there when there were a few sunspots, so he didn't get much data. So it just kind of fell into place that our data set starts at 1749 and the first solar cycle started in 1950. Rudolf Wolf also developed the equation on how we count sunspots. And there's a little formula there. It's the daily sunspot number is K. K is a fudge factor. Depending on your observatory, you know, you got to remember, telescopes back in those days might not be real good, and there's probably some difference in them. G is the number of sunspot groups. You know, sunspots come up, there are groups of them. And of course, each group has individual sunspots too. And that's what the S is, the total number of sunspots. And that's how we calculate the daily sunspot number. Unfortunately, humans count sunspots. A subjective measure, you know, 10.7 centimeters solar flux. Well, that's measured, you know, and assuming the calibration on the receive antenna is good, you know, there's no human bias to that. And that, I don't think I have a chart on that, do I? No. You saw in some of the other plots, when I said smooth sunspot number, there was a parentheses, V2, that's version 2. Okay, the old version is version 1. In the 1990s, concern was how good is our old record in sunspots? So there were 4 workshops that went through all that. There's a new sunspot record, and the sunspot numbers have increased. What the biggest problem was when Rudolf Wolf retired from counting sunspots, there's a guy named Wolfer. He took over, and he had to multiply his numbers by 0.6. Agree with Rudolf Wolf's numbers. And that 0.6 factor was carried all throughout time. And it was determined by those solar scientists that, well, the original numbers were better. So that's why we have 2 records right now. You got to watch it, because what do you use in the propagation prediction program? Sunspot number. Unfortunately, the propagation predictions were developed using the old record. So, you know, you got to watch it if you use the new record. Here's just a general picture of what the ionosphere looks like on a day. The equatorial ionosphere is the most robust in the area in the world. The red lines are critical frequencies for the F2 region. In other words, critical frequency is what's the highest frequency you can send straight up and it comes back down from the F2 region. And you can see the equatorial regions really are blessed. As you move farther north or farther south from the equatorial regions, the MUFs go down. That's why a lot of days I can listen on some of the bands. The guys in Texas and Florida are working stuff, and I can't hear anything. So you're in the same boat up here. So if you want better propagation, move south, okay? Okay, next several years. What is just a little summary of what to look for. 2 things have to happen to make a QSO, right? The MUF's got to be high enough, maximum usable frequency, to refract the signal back to Earth, and the loss over the path has to be low enough so you can either hear it or your computer can decode it. The lower bands, well, what's important on the lower bands, 160, 80, 75 are 60 meters too, is the absorption in the D region. That's part of the loss. Yeah. That is critical on those bands. The MUF is usually not an issue because it's usually high enough for those bands, regardless of where we are in a solar cycle. So that's why absorption on 160 and 80 are really critical. They're best around solar minimum. They're good at night for DX contacts. Of course, thunderstorms don't help, but that's why they make receive antennas. And also keep an eye on sunset and sunrise at your QTH and the other guy's QTH, because there can be some good enhancements on that. There's a general consensus amongst top banders that 160 just hasn't been as good as it has in decades past. And there's a lot of stuff going on in the Earth-Sun system. You know, we got climate change, CO2 going up, and CO2 can produce electrons down in the lower regions of the ionosphere, like the D region, which does not help. More electrons in the D region means more absorption. So there's stuff going on that we just don't fully understand yet. And there could be other things too. On the higher HF bands, we're in a great place right now, fall and winter. The amount of F2 region ionization is the critical factor. Absorption is inversely proportional to the square of the frequency. So the higher the frequency, the less the absorption in the D region. And that's why absorption is really not an issue in the higher bands. And like I've said a couple times, great worldwide propagation during the fall and winter months. Of course, those lower MUFs in the summer, well, hopefully sporadic E will come mitigate that a little bit. Then we got the middle bands, 40, 30, 20, 17. They're kind of good throughout a solar cycle. 40 and 30 mostly at night, 2017 during the day. I've always believed if you can only put up one antenna, put up a 20-meter antenna, because that would do you good throughout the whole solar cycle. Well, okay, summary, cycle 25 is leveled off. It could go a little bit higher, but don't know. We'll just have to wait. If cycle 25 stays kind of down there, that kind of suggests maybe cycle 26 is going to be smaller, because it says we're kind of in that third period of smaller solar cycles. We'll see. Of course, the digital modes offer an advantage over CW and sideband. Because, you know, the digital modes, their IF decode bandwidth is they can narrow up, less noise gets in, so they can hear signals farther down. That's a big advantage, and of course the whisper is the biggest advantage. And FT4 I think is kind of in there somewhere at the top of, it helps, but not as much. FT8's right now is in a good place, and you can imagine if you ever look at the club log statistics, in 2017 FT8 just took off. It just dominates amateur radio now over the combined CW and sideband QSOs made. So that's how amateur radio is going. That's our evolution, I guess. More technical, more digital stuff. Take advantage of the summer season if sporadic E occurs. And of course, there are tools on there in the internet to determine what bands are doing right now. One of my favorite is dxmaps.com. You can pick the band, you can pick the world view or North America view, and it'll show you who's working who on the paths. And if you go there and there's nothing happening, no use getting on. If you go there and you see all kinds of red great circle paths from here to there, hey, things are going on, you might want to see what's going on. PSK Reporter does the same thing, WhisperNet does the same thing. The reverse beacon network is where you transmit in a certain format, then you can go listen to SDRs, software-defined radios around the world, and see how your signal is over there. So that gives you a pretty good real-time picture of what the ionosphere is doing right now. Okay, that's all I had. Anybody got any questions, I can try and answer them. If not, I just thank you for attending. Okay, yes?
Sometimes there's propagation conditions that seem to be one direction.
Yeah.
Or they're much, my signal is, I'm hearing this guy really well, and
Yeah.
he just barely can pull me out, and vice versa.
Yeah.
What's going on with that?
Well, there's a couple things. I'm not sure we fully understand it. One is how much power, is each station running. That could be 100 watts, 10 watts. It's 100 watts, 1,000 watts. That's 10 dB, so that's quite a bit. The noise environment at your QTH, that could do it. Maybe you've got more noise than he does. I think the ionosphere has something to do with it too, but I don't fully understand it. As an example, I've had the same thing on 160. There's a gentleman in New Mexico, WD5COV, and during one of the contests, I kept calling him. He had a great signal. He just CQ'd in my face, what's going on? So something else is going on. I know he had good receive antennas, so he probably didn't have to worry about his noise. I was probably running the same amount of power as he was, but there's still something going on, and those things happen, yeah. How's that for a definite answer?
Could it be the soil or?
Yeah,
People say like Texas is all sand.
yeah, the ground conditions, of course, will determine your pattern, the elevation pattern. Of course, that's most important for vertical antennas. So if some guy's got a really good ground with his vertical on 160, he's gonna probably put out a better signal than me with my vertical over, just average ground. So yeah, that's a good point. Okay. Oh, yes.
The comment about 160 now.
Yeah.
Is there any evidence that noise levels are coming
Yes.
up?
Good point. Good. Glad you brought that up.
Traffic department is buying the
Yeah.
cheapest traffic light controllers they can
Yep.
buy.
Yes.
And they radiate crap
Yep.
all over.
Yep. Back in the 70s, the ITU developed patterns of man-made noise in maps. That was 1970. We didn't have a lot of computers back then. There was a group in the Netherlands, the Netherlands Amateur Radio Organization. I think it's VERON or something like that, whatever that is in Dutch. But they determined that, yes, the noise levels are higher around the world. And it's significant on the lower bands. So that could be another factor why 160 meters just doesn't seem as good as it used to be. So there's man-made issues. There could be climate issues. There could be other stuff. But, yep. I'm not sure we can, we can't do anything about either of those, really. So, unless you move out into a very rural area.
Using computer modes instead of.
Yeah, use your digital stuff. Use the digital modes, yeah. Okay. All right, thank you very much.